panel. So this next one is about a mechanism which is question answering. Sorry, I thought I got it down, but it's I think I can talk from this one now, right? And some of the catalyzing questions that we have this time are: would the same knowledge representation be good for describing mechanical mechanisms and question answering? Why or why not? What kind of knowledge is required to answer what-if questions about the mechanism? And what kind of mechanism could produce knowledge from observation that would be useful for question answering? So, who wants to go first?
Okay. Well, when you say question answering, that seems to me a really broad area, which would include questions like, what would happen if I pulled this switch on this mechanical system? So yeah, I think you do have to have one knowledge representation system that is able to handle mechanical systems in order to have a general question answering.
I think maybe I'm wrong, but what this might be getting at is a sort of a contrast between sort of text-based, like question answering often is like you read a lot of text and then you get some natural language question about it, versus maybe mechanisms where you have a sort of causal model of the components and how they work together, which and then the question is like, should that be different? But you were already answering, but I would like to maybe clarify it a little.
Yeah, so I think there are for example, visual question answering. That's the area that I'm most familiar with, where they take an image and a question and they say, looking at the image, answer this question in English. And the usual way that they solve this problem right now is by training neural networks and evaluating the frequency that they get the correct answer. But since they have no mechanical knowledge encoded, they aren't really able to perform deductive reasoning about how things would happen. I think there's a ceiling on how well that kind of technique would work. So ultimately, to really be able to answer general questions, I think you do have to have a knowledge representation that includes all of them. Do you want to go question by question, or should I?
Well, but AXE can answer every question without any knowledge representation.
Eventually.
I have very little intuition about what's going on in AXE.
You can give it to somebody else if they want to answer it. Maybe if we could keep the individual answers relatively short, then we can go through all the questions and have some variety in who is talking.
It's indeed a very broad question, and in mechanical mechanisms, if we mean talking about objects and state transitions and these mechanisms, then the answer questioning in language, if you stick to this object representation or in language, then you could answer those type of questions. But in the general context, it's not very compatible with what is, in my opinion, with mechanical mechanisms.
So, in my opinion, and I'll keep this short, to really have an understanding of something, you need to have pretty good models of that thing, and you can cheat on, say, you can create a bot that can answer, seemingly hold a dialogue without that thing, that program understanding anything. It's much more like a rock rolling down a hill than a person or an animal thinking about something. A dog that alerts its owner to the child that fell in the river, etc. I think these are very, very different things, and they really, the main difference there is that there are, in the entity or the agent that understands, there are models that allow that agent to to run simulations to predict what's going to happen based on its models of the world. And I'll leave it at that.
Okay, my approach. I make a vacuum cleaner robot go online and ask questions about whatever it is told to do. And as a mechanical thing that the robot can do, well, it's a trick like a chatbot, but it can do one thing. It can go physically and start cleaning. So if it is forced to be grounded, like the cleaning as a word is grounded, and it knows that it can do. And the other, like perception, I don't know, like sensors tell that the baby is sleeping or there is somebody is studying for the exams. It can go online and ask zillions of questions. What is going on if I start now, or if I really need to do cleaning? So if somebody says, I don't know, some slang word, like, I don't know English slang enough, but just beat it, for example. So it can go online and check what people do when they are told to do it. Of course, they are angry, but if there's something I can do, or maybe clean, no, there's no cleaning, so no mechanical knowledge about it, but nothing that I can do about it, so it can ignore it. But if it's, this room is a mess, it can go and see if there are some actions that people do, and it can maybe guess what to do. That's my approach, but it's nothing really about understanding. As a user, if it goes and cleans after I say this room is a mess, for me, it understood, but I know it's not a popular opinion.
You can go on to the next question if you want, or
Sure.
Or we can take questions from the audience if there are any. Oh, I guess free from.
So, for answering questions about a mechanism, you think about a cup of water being turned over on a desk and washing something away. You can imagine what would happen in that situation, but your brain isn't really running a simulation, a particle physics simulation of the fluid flow. And yet it seems like there's more going on than just the sort of logical deduction that would happen in a psych-like system. I think understanding a mechanism means having some kind of ability to predict what the future state is going to look like based on the present state that is informed by experience, and maybe can't be carved down into these symbolic terms and their relationships.
Yeah, maybe from my understanding, the understanding of a mechanism, or is actually in general, is in that sense mainly, I think, also some kind of meaningless. It's also understanding is also the degree in which it is a useful representation of what actually the goal of the system is. So also understanding is in that sense gradual, and it also depends on whether this information is useful to do actually the work that the system is able to do. And in that sense, what if questions are, in my opinion, easier than answering questioning type of thing, because in what if if you have a good or understanding of the process, then you could make predictions about what will be the case if certain things would happen. But I think also part of the understanding is understanding how well the information, what the quality of the information or the influence of the quality of the information has on the actually achieving the goals of the system. So it also needs to understand what the effect of certain transitions and mechanisms is on in terms of uncertainty, and how that influences also how well the goals of the system can be achieved.
Oh, you have a question? Go ahead.
So, if you're trying to understand the mechanical mechanisms, would that be good for understanding analogy or metaphor or similarity?
So this relates, in my approach, this would basically mean how good is your representation of models? Is it any good for computing similarity? And if so, how do you compute that similarity? And it's a very good question, because I think that's really at the heart of transfer learning, and cumulative learning cannot be implemented in any other way than having a decent mechanism for similarity evaluation, because that really tells you how relevant your current knowledge, i.e. your best models that are most similar to the current state of affairs, whatever it is you're trying to do, if they're really far away from being similar, then you know they're not going to be that good at predicting what will happen. And so that's basically the basis of you tapping, if you're a robot, tapping your owner on the shoulder and say, hey, I don't really trust myself to do this because it's just so different from everything I've ever seen. Analogy, I think, is similar, but not exactly the same. Yeah, I'll leave it at that, and we might come back to that. Someone else wants to.
Yeah, maybe for similarity, it's also that from understanding the system, I think it's also important, again, that in the way in which certain things are similar or not has an effect of finally the goal of the system. So it's only, in that sense, it should also realize, if it understands the difference between different entities, whether that really has, whether that the difference really has an effect on the system reaching its goals.
If I had to make a system that was going to predict how a visual scene would evolve over time, I think that the way I would do it right now is to train a neural network on short videos, and then have it try to generate what the future scene would look like. And to the extent that the neural network is able to build hierarchical representations that can find a similarity between the current scene and the scenes that it's seen in the past, then it would be able to form a correct analogical picture of what the future would look like. I'm not sure if that exactly answers your question, but at least it has all of the same words in a different order.
It's just a great AI thing.
Okay, I've been working with metaphors for quite a while. They're tough, but as I said during my talk, if you give lots of context, like for example, if I tell you, okay, the dog came to its head, which is a Japanese idiom, you will not really guess what it is. But if I give you like 10 examples, then you probably will understand, okay, he's angry, it is angry. So, well, that's how I deal with metaphors. I just give a lot of context. And in case of simple things like Roombas, it's easier because the search space is smaller. It can, it knows not so much about the world. So well, sometimes it works, sometimes it doesn't.
Maybe to explain a little bit more about the similarity. If you have a system which has a certain goal, and you have a mechanism in which the system can derive from its goal how good the certainty or uncertainty of certain models or certain processes should be in terms of similarity. You can derive an uncertainty about or certainty about those models. So you could in fact derive how similar certain entities should be to generate the same effect or the same quality of goal. And in that sense, you could let the system itself define how similar certain things are or should be.
Do you think that being able to answer questions about a mechanism is sufficient proof that you have truly understood that mechanism, or would you expect some other criteria like being able to use that mechanism? Or anyone?
Again, I think being able to answer questions is so general that you could map any other task that you want to onto answering questions, and therefore that it would include it. So that question could be, what do you imagine would happen if such and such situation existed, and then in order to answer it,
the question would be, what exact series of steps would you take in order to build this machine using these tools, right? So,
right.
Yeah. Yeah, I would, again, slightly different sort of question, more aimed at building stuff. So when I think about how an OpenCog system, for example, just because that's the AI system I'm most used to thinking about, would answer questions about mechanisms. Now there's two very clear approaches I could take, and it seems like in my own mind as a human, I'm often taking a different approach than either of them, right? So I mean, one very clear approach is you're using logic, basically. So you have some logical, structured knowledge about the topic, and you're just using logical inference to answer the questions, right? And that it will work if there's enough logical knowledge there. And in theory, you could encode any mechanism, no knowledge about it, in logic and just do reasoning. Sometimes that is what I do introspectively, often not. Now, another thing you could do in an AI system is actually build an accurate simulation model, right? I mean, you could put a physics engine inside your AI system, much better than anyone that the human brain has, and actually construct a model of that mechanism. I mean, like say the AI saw a machine in front of it. I mean, it can interpolate from what it sees and build a physics engine. You build a model inside its physics engine and just run it, right? And doing that, you would imagine an AI could answer questions about mechanisms a lot better than a person can, because unless you're like a crazy idiot savant genius about it, you're not able to like construct a detailed model of a Rube Goldberg machine or a car in your head. Like if you're an auto mechanic, you will get that model in your head eventually after many years, but we don't get it immediately, as it seems like we could if we just saw the machine and knew the principles. On the other hand, what's interesting is it seems like often when reasoning about mechanisms in my own mind, I'm using some sort of like pseudo-physical model in my mind's eye of the mechanism, but it's not really an accurate physics engine model, but it's also not really just like a logical model or something, right? Like if I think about a car's engine, I mean, I envision in my mind's eye, like there's some pistons, there's a carburetor, there's these tubes coming out the back. They're sort of connected in vaguely the right way. They look like something, and the pistons are pumping up and down, right? And then I'm using like a mix of logical reasoning and maybe inductive patterns and some geometric reasoning, maybe a little bit of thermodynamics or Newtonian mechanics, but both with a lot of errors, right? So I'm like cobbling something together at the intersection of language and physical modeling and analogy reasoning. And I guess the question from an open cognitive that I have is like, how do I want to implement something like that, right? I mean, an open cog, it would have to involve some nodes and links in the symbolic atom space, something in the some nodes. You have to involve some nodes and links in the atom space, which is symbolic. It would involve some activations in some deep neural net, which was like giving an image of the pistons going up and down. But then for like vague geometric layout, I'm not quite sure what I would do, because you could put it in a simulation engine, but then you're giving a precise geometric layout, and maybe that's fine, even though it's not what the person does. You could also work up some representation that's more topological than geometric, but what's funny is in my mind's eye, it's mostly topological, but a little bit geometric somehow. So I guess to do this in OpenCog would be a bit of a hack, and maybe that's all right. Maybe it'd be a cognitive synergy hack, right, where you have different parts and different components of the system, and they're all kind of coordinated together. Or maybe there's some more elegant, like, theory of this type of intermediate mechanistic reasoning. So yeah, I'm curious how others would think to deal with that in AI systems.
So in my talk yesterday, I mentioned about trains of thought and chains of reasoning, and that our trains of thought are not necessarily an actual reasoning chain. That there's different kinds of links between ideas. So I think that, although I haven't yet built it, that the high-dimensional vector space representation of concepts, that you could have one concept for a visual image, and it would have a transformation that takes it to a new visual image, and find a series of these that gets you from the original visual image to where you want to go.
So you think like the image in my mind's eye I have of a car's engine, I should represent as a high-dimensional vector?
Well, I think it could, that the high-dimensional vector representation would be capable of uniting reasoning and visual transformations in a way that is more natural than the hacky system that you're
I completely cannot see how that could make any sense at all. So maybe if you could explain in more detail, it would be interesting. I'm very familiar with dimension reduction representations, but I don't see how the operations carried out by a car's engine while it's doing stuff will be naturally represented in terms of a high-dimensional vector representing the car's engine. Like when the pistons are moving up and down, or there's some air blasting out of the exhaust. Like how is the vector representation mirrored that?
Right. So imagine you have a neural network that has looked at lots of pictures of engines and has got a hierarchical representation in its weights of the engine at various states.
So it's a recurrent neural net that simulates the dynamics of the car engine.
Something like that, yeah. And so if you take all of the weights of that neural network at one particular time and call that's my semantic vector of the state of the engine at this point.
But it's very low level then, right?
Well, parts of that representation are low level. The ones near to the pixels, but at the high levels of the neural network, you've got something more similar to a concept, right? That you can find similarity between one engine and another engine.
Yeah. So like if you're training like something like an infogan network with some structured latent variables, which is a recurrent neural net, rather than just a hierarchical neural net. I mean, I guess it takes a lot, as you know, it takes a lot of very special machination to get there to be variables that have any semantic meaning, and no one has done that for recurrent neural nets yet, but they will. I mean, that's interesting. Yeah. So then I agree. If you trained a recurrent neural net with some like structured probabilistic latent variables or something, by repeated observation, unsupervised, of some dynamical system, you could hope that those high-level variables will correspond to like how fast is the engine running, or how much smoke is there, how fast are the pistons going up and down, right? Just like if you train an infogan model on faces, the emergent latent variables will be like how big is the smile, or how bushy are the eyebrows or something.
But we're still several years away from being able to do something like that.
Yeah. But that still isn't quite as like topological as the image you have in your mind's eye when you think of a car engine, right? It seems like maybe it feeds into that, but isn't quite that. No? I would love to hear from Kristinn how Era will deal with that.
Yeah, so this is really the question of what kinds of models does the system develop when it acquires knowledge.
Specifically about mechanisms, yeah.
Yeah, it will, well, in Era, there are, models are very, very small, so they can refer to basically two tiny variables and a single value on each of those variables, bounded by time and composed, being part of an enormous hierarchy that together has some meaning to the system, basically, while still being decomposable to those really tiny peewee size models. And this is really a lot of what comes to my mind when I try to explain this system has to do with how the system acquires these models, because this is really a requirement of AGI. So for AGI, in our view. So your question is more, let's say, focused on once the system has acquired some sort of knowledge represented by these models in a model cluster, what would that look like? But basically, it always looks the same way. It's more or less a fractal kind of picture that emerges. It's basically that.
Well, everything looks the same if you're far enough away from it,
yeah.
but the structure must be different for modeling a mechanism than for modeling a sentence.
Yeah, not really. I mean, basically, everything is temporally bounded. Models have a context in which they're relevant. Model clusters have a context in which they're relevant, and so on. And so, because models are hierarchical, they refer to subclusters. So there can be, just like Pei was saying, you can have multiple representations of what appears to be the same thing. I mean, the cup, when you break it, it's still the cup, but now it's broken. But a new phenomenon emerged, which is actually the pieces. So the word we use for the parts of the cup when it's broken, we never used that when the cup was whole. So before the cup is broken, you don't think about the pieces because you don't know what they are until you break the damn thing. And when you break it, now the pieces emerge. So now the context for that model cluster of what are pieces of a broken thing like emerges basically from the context. When you look at that thing, it's lying there. This is how Era brings out the relevant models for that scenario, and this is how. In fact, it's about similarity. It's like the models that seem to represent what's before your eyes the best emerge or sort of rise to the top automatically due to the scheduling of the whole system. But this is, this is the best I can do in about 1.5 minutes.
Okay, let's thank our panelists.